Hello, everyone. Welcome to pre-lecture 9. This will finish up our at least pre-lectures for kinetics in chapter 12. We'll be talking about reaction mechanisms. And so for a chemical reaction to occur, we essentially have three things that need to happen. And so first of these is that the molecules must physically collide. This hopefully is obvious that we can't have a chemical reaction unless they actually touch. The collision between the two species, in our example here, that's A and BC, must occur with sufficient energy such that the bond between B and C breaks. So there must be sufficient energy. Lastly, they must be in the correct spatial orientation. And so, for example, if A has to hit the side of the molecule where C is in order to form AC, if A were to approach this side of the molecule where A instead hits B instead of C, then a chemical reaction would not occur. Okay. If any of these three criteria are not met, then the chemical reaction will not occur. So you need all three in order for a chemical reaction to happen. Okay. If we think about this in terms of a reaction with actual chemicals, say we have NaCl and 2 moles of that, they would need to collide to make 2 moles of NO, 1 mole of Cl2. Okay, so you could have an effective collision in these two ways, pardon me, but if you get the two Cl's to bump into each other, then you would have an effective collision that would allow for the reaction to actually occur. Okay. One way we measure this is called the frequency factor. So this is signified by the variable A. This addresses how often successful collisions will occur. And that is, A can also be broken down into an orientation factor, which we designate P, and the frequency of collisions. And so the frequency of collisions will be determined by the temperature, right? Because the more kinetic energy something has, the more frequently gases are going to collide with each other, okay? Or orientation factor is something that represents a fraction of the collisions with the orientation that allows for the reaction to occur. And so if 100% of our collisions are always correctly oriented, say if we have one of our reactants is just a sphere, then our P would be pretty close to 1. And if we have more complex reactions like the one shown above, then P would be quite a bit lower. Okay. And the frequency of the collisions, again, is based on temperature, but also then pressure and volume. Okay, and that is something that we'd have to measure. Right? Some other things that may affect the rate of a reaction are the physical state of something. And so say a reaction has to occur on the surface of a solid. Obviously, things with more surface area will lead to faster reactions. You also need to consider temperature, concentration, and the presence of a catalyst. And you may not know what a catalyst is yet. We'll be covering that in class. Okay. So also, if we think about a reaction occurring, they have some amount of potential energy in our reactants and some amount of potential energy in our products. But in order to go from reactants to products, we need to overcome something called an activation barrier or activation energy. You can state it both ways. Okay. And we need an activation barrier, otherwise the reactants would instantaneously turn into products. And so essentially when a reaction occurs, we're measuring partly at least the activation energy in order to get to the transition state. And then we can have an activation barrier for both an exothermic reaction or an endothermic reaction. The only difference there is whether your reactants start with higher energy or lower energy relative to your products. Okay. Right. Typically speaking, the higher the energy of an activation barrier, the slower a reaction will be. And at the top of our barrier, we get what's called the transition state. And this is the state where bonds are actually formed or broken. And by definition, this transition state cannot be isolated. This is not something we're ever going to see, but it is something that can be speculated and reasoned out. okay? All right, so if we're looking to quantify these kinetic relationships for how fast a reaction goes, we tend to use what's called the Arrhenius equation. And so this relates our rate constant K with A, our frequency factor, our activation energy, this E sub A term, and then the ideal gas constant and a temperature, okay? E is our lowercase e is the constant E, okay? One thing with this, make sure your temperature is in Kelvin so that it matches our constant, which is units of joules per mole Kelvin, okay? If we perform the measurement of K, essentially if we measure the rate at multiple temperatures, we should be able to form a linear Arrhenius equation to determine the activation energy, which will be the slope of a line of negative activation energy over R, which is our gas constant. We can also use this relationship to calculate A, which is again our frequency factor. If you have multiple rates and temperatures, you can use a 2-point form of the equation as well, where this is what we would commonly use and what we will use in lab this semester in order to estimate our activation energy, okay? Right, so within each reaction, we also have what's called a mechanism. And so many chemical reactions take multiple steps that will be actually two distinct reactions taking place in sequence. And so we call this a reaction mechanism usually that detail our step-by-step process. And so for example, we have the decomposition of ozone, which is O3. And so it's two elementary steps. Basically, when we break down each step in a total reaction, we call those elementary steps. We have O3 forming O2 and just O, and then another equivalent of O3 reacting with that O to form a total of 2 moles of O2, okay? So that is our reaction mechanism, or rather the elementary steps. We also form an intermediate. And so anything that shows up as a product in a first step and then is consumed as a reactant in a second or even later step makes it an intermediate. It is not something that we write as either a reactant or a product. As the name would imply, it is an intermediate. So the overall reaction is 2O3 yields 3O2, okay? Right, and so suppose we had this reaction here where we have NO in equilibrium with N2O. In the second step, we add in H2, we form these species, and in the third step, we go on there. And I ask you here, what is the overall reaction that occurs? What intermediates occur during the elementary steps? And write a rate law for step 2. And so I would encourage you to do that. We'll go over this in class again, but take some time to practice this. This could be a question that shows up on a quiz or a similar question at least, okay? Right, so within each mechanism, one of our steps will be the slowest, and this will be called the rate determining step. And so I like to think of this as an analogy. Say we're in Southern California, we have a 4-lane highway closing down all but one lane. That will create a bottleneck where only one car at a time can get through. And so if we shift that into chemical terms, say we have NO2 plus CO yields CO2 plus NO. At temperatures above 225 degrees Celsius, this would be our rate law, whereas below it would be K NO2 squared. Oops. And so we would have a 2-step reaction here where we have this first step where we form NO3 and NO, and then NO3 plus CO2 yields NO2 and CO2. And so we would change our mechanism and our rate determining, or rather we would change our rate determining step at different temperatures, okay? And we could tell that depending on the rate law. So yep, that's just something you should know. And the rate law for the overall reaction will be determined by the slowest elementary step, as they will be the same, okay? Right, that's the end of our pre-lecture for today. Hope that was helpful. If you have any questions, please let me know or come ready to ask them in class. Take care.